Hello everyone, I'm Pragya Kaur, and today I'll be presenting our work ExpresSense, exploring a standalone smartphone to sense engagement of users from facial expressions using acoustic sensing. Facial expressions have been studied as one of the true indicators of mood, anxiety, and cognitive functions like human attention and engagement. Facial expressions can be used in various assistive and ubiquitous systems, ranging from anxiety detection, mood prediction, engagement detection, expression-based interactions, and so on. Thus, several existing approaches have developed vision-based techniques for detecting facial expressions. However, such systems are often affected by ambient light, facial angles, and occlusion. Moreover, the systems might lead to users' discomfort by invading their privacy. In this regard, our vision is to develop a system that does not require a camera or any additional hardware and can run on a commodity smartphone while handling various environmental factors. With this vision, we first pose a question: is it possible to sense the user's facial expression without watching it? In particular, we aim at understanding whether acoustic sensing can be employed for detecting various facial expressions of a person on a commodity smartphone. While answering this question, we make the following contributions. Firstly, we develop a lightweight smartphone application called ExpresSense that uses near-ultrasound signals for detecting users' facial expressions. Secondly, we evaluate the core model under robust setups and further develop an application of ExpresSense to analyze its performance under realistic setup. Previous works have focused on the development of indoor localization techniques, coarse grain movement tracking like fall detection, signature gestures, etc., using frequency modulated continuous waves, FMCW. Acoustic chirp signals have also been used to detect instances of eye blinks, as blinking instances have been found to cause major shifts in signal features. On the other hand, some existing works have used commercial and custom-built devices like microphone arrays and earphones to detect people's facial expressions using acoustic sensing. Since our aim is to facilitate expression detection with a smartphone only, we conduct a pilot study with two participants. While placing the smartphone at about 30 centimeters away from the subject's face, we played FMCW signals with a sweeping frequency of 16 to 19 kilohertz through the smartphone speaker and then captured the reflected chirps through its microphone. During this, the participants performed some sequential facial actions like raising eyebrows, blinking, raising the cheeks, moving the mouth, and smiling. By analyzing the phase and amplitude of the recorded signals from the selected frequency bin, we observed that each facial action caused a significant variation in the feature values. This has been shown in the figure graphically. By identifying this opportunity, we've also estimated the challenges associated. For example, commodity smartphones support near-ultrasound signals and hence allow the usage of signals between 16 to 19 kilohertz to ensure that the signals are well above the audible range. Similarly, the availability of single microphones, infeasibility of fused signals, requirements of identifying distinguishable patterns for expression classification, etc., are some of the major challenges to be addressed while developing the system. With these observations, we then develop the core model of ExpresSense that transmits these chirp signals with an optimal duration of 14 milliseconds through the earpiece speaker of the device. The reflected signals are captured through the microphone and processed in the device. In the processing stage, the transmitted and the received signal delays are removed through cross-correlation, followed by a template subtraction for static interference cancellation. This is followed by selecting the frequency bin with the highest variance in phase, which corresponds to the facial region of the person. The phase and amplitude of the signal with the selected frequency are then calculated and sent to the assembled classifier using majority voting from the logistic regression decision tree and random forest models. Finally, the facial expression is classified as either anger, happiness, sadness, or surprise. We evaluate ExpresSense to answer the following research questions. Firstly, we try to find out how well our model can classify the facial expressions. For this, we conduct a lab-scale study with 10 participants. The participants were asked to place their phones at about 30 centimeters in front of their face in an indoor environment. They participated in 3 different sessions. In each session, they reproduced the 4 basic facial expressions, each for about 1 minute. The ground truth were collected by comparing the manual label entered by the participants in the application and the expression detected by a trained mobile net model from their facial videos. Moreover, manual inspection was employed to ensure the validity of the produced expressions. Apart from these sessions, we conducted additional sessions under varying conditions like distances, angles, sound, motion, etc. to answer the next research question. In total, we collected about 6,880 data samples from these sessions. By analyzing the data in an overall intersession and intra-session basis, we found out that within session expression predictions are slightly more accurate due to the lack of involuntary positional and angular shifts. The figure to the right depicts that ExpresSense can classify each expression with significant accuracy. To answer the next question about whether environmental factors affect the performance of ExpresSense, we analyze the data collected from the additional sessions. We can see that as the face to phone distance increases, there is a 6 to 14% drop in the average accuracy. Next, we see that elevation from 0 to 45 degrees has no effect on the performance. However, the accuracy drops at negative 45 degrees. Interestingly, various tilting angles of the phone had no effect on the system's performance. Since we use near-ultrasound signals, ambient noise does not affect the performance either. Since bin selection is a one-time process in the current version of the system, major body motion decreases the performance of the system. Hand placement at 0 degree, that is palm towards the bottom, covers the smartphone's microphone and hence affects the accuracy. However, finger motion, surrounding objects, and presence of glasses did not hinder the performance of the model. Next, we estimate the performance of ExpresSense under natural expressions. For this, we develop a video streaming application that allows the user to play videos of different genres while ExpresSense works in the background, predicts their expressions, and generates an engagement estimation, as shown in this figure. The engagement score is generated by correlating the video genre with the frequency of the relevant expressions during the video. For this experiment, we asked the previous 10 participants and additional 2 participants to naturally watch 15 YouTube videos from different genres like comedy, anger, tragedy, horror, and mixed. These videos had different durations ranging from 7 to 30 minutes. Based on the predicted expressions, ExpresSense generated the overall engagement score and the overall engagement indicator of each of the participants of the video. For ground truth, we conducted a manual interview where the participants were asked to answer numerous questions from the video after watching each of them. This was followed by a self-assessment of engagement and interest. By comparing the predicted and the true scores, we found a significant correlation between the two for the participants for whom the model was trained. For the overall engagement indicator, we can observe that the system performs with high precision recall on F1 score. Figure 13 proves the system's capability of distinguishing the engaged participants from the disengaged ones. To answer the final question regarding the system usability, we deployed the application and asked 72 users to use it and provide a feedback based on the system usability scale. The system achieved an average score of 85.3, proving its high usability. To conclude, we present a system ExpresSense that can detect facial expressions using near-ultrasound signals on a smartphone. Although the system can be improved through recalibration to handle obstructions in motion, it performs well under robust setups with significant accuracy in its current form. Such a system can be used to estimate users' engagement and can be accepted globally for various other applications. Thank you.